how the simplest laws of physics, really, can let us move mountains.
Or at least, things that feel like mountains.
Mhm.
Huge excavators, massive cranes, all with what seems like very little effort.
Exactly. And that's our deep dive today. We're talking about the foundational trilogy of physics: force, pressure, and area.
That's right. The goal here is to really unpack the math that underpins every single hydraulic system. If you can master one simple formula, P equals F over A, and understand the unit conversions, you're set.
The big one being imperial versus metric, which trips a lot of people up.
It absolutely does. But once you get that, you hold the key. You'll understand how a relatively small pump can generate just enormous leverage.
So our mission today is to get past the textbook definitions, find those aha moments. We want you to walk away actually getting the trade-off that happens with mechanical advantage.
And then see how that exact same math is used in more advanced tools, like pressure intensifiers. We'll hit the units, we'll clarify that core formula, and then we'll see how just manipulating area gives you that incredible power.
It's elegant physics, really.
It really is.
Okay, so let's start at the beginning. Let's start with force, because without it, nothing moves.
Right. Force is, at its core, very simple. It's a push or a pull. It's anything that tries to change the state of something, whether it's at rest or already in motion.
And this is where the confusion starts right away, especially if you're working on, say, international projects. In the imperial system, force is measured in pounds, L.
Which sounds straightforward. The problem is we also use pounds colloquially to talk about weight or mass, and they aren't quite the same thing.
Which is what the metric system cleans up so well. In metric, force is measured in newtons, N.
Yeah, and that distinction is so important because the very definition of a newton is tied to acceleration. The formula is force equals mass times acceleration. F equals m times a.
Right. And for what we're talking about, lifting heavy things, that acceleration is gravity.
Exactly. The acceleration is due to gravity, which is 9.8 meters per second squared. This is the one step our sources just hammered home. You cannot forget it when you're converting from a mass to a force.
So here's the first big takeaway. A mass of 1 kilogram, just sitting there, exerts a downward force of 9.8 newtons.
Right. So a 100-kilogram load isn't 100 units of force. It's 980 newtons of force pushing down on that piston. You have to cross that bridge first before you can do anything else in the metric world.
You cannot skip that step. Okay, so from the force being applied, let's talk about the space it's applied over. Let's talk about area.
Area is much more intuitive. It's just the amount of surface inside a boundary. A square inch, a square meter.
But the units still matter. Imperial systems are pretty much always using square inches in squared.
And metric uses square meters, m squared. But here's a little practical tip. If you're working with smaller components, like pistons or seals, you'll often see square centimeters used in Europe, even though the official SI unit is the square meter.
So always double check your units before you start plugging numbers in.
Always.
Okay, so we have force, we have area. That brings us to the third piece, pressure. The synthesis of the first two.
Pressure is the concentration of that force over that specific area. And this idea of concentration, that's the whole secret to hydraulics.
And the units for pressure tell you that right away. In imperial, it's pounds per square inch, PSI.
Exactly. Force per area. And in the metric world, you'll usually see kilopascals, gash, kPa, or bar.
So to set the stage for how this all works together, if you have a 100-pound load pushing down,
you need 100 pounds of fluid force pushing back up just to hold it in place, to be in equilibrium.
And if it's that 100-kilogram mass,
then you need 980 newtons of fluid force pushing in the opposite direction. Simple balance.
That balance brings us right to the core formula of this whole deep dive. Pressure, P equals force, F, divided by area, AP equals F over A.
That's it. That is the Rosetta Stone for all of this. And, since it's a relationship, you can just rearrange it with simple algebra. If you need to find the force, it's just area times pressure.
And if you need to find the area, it's force divided by pressure. Simple, but so powerful.
It is. But you mentioned something earlier, and our sources really focused on it. That conversion from mass to newtons, is that really such a common mistake?
Oh, absolutely. It's probably the #1 error when you're looking at specs from different regions. If you forget to multiply that mass in kilograms by 9.8, your entire calculation is wrong by, well, a factor of almost 10. It's a huge error.
So let's talk about the actual metric unit of pressure, the Pascal. press.
Right. 1 Pascal is defined as 1 Newton of force spread out over 1 whole square meter.
Which is, as you can imagine, a tiny, tiny amount of pressure.
Just minuscule. I think 1 Pascal is something like 0.000145 CSI.
Exactly. So if you tried to rate industrial equipment in pascals, the numbers would just be astronomical. You'd be in the millions, billions. It's useless.
Which is why we always see it as kilopascals, or kPa, 1,000 Pascal.
Right. Or sometimes you'll see the bar, which is roughly 100 kPa, or just a little under 15 CI. They're just more manageable, useful numbers for engineers to work with.
That's great context. Okay, let's get to the magic. The influence of area. This is the aha moment.
It really is. So let's imagine we have a constant force, let's say 100 pounds.
Okay.
In scenario A, we apply that 100 pounds over a big area, say 100 square inches.
So P equals 100 pounds divided by 100 square inches.
This gives you just 1 CI. That's nothing. You can barely feel that.
But now, scenario B. We take that exact same 100 pounds of force and we focus it. We put it all on a tiny area, let's say 1 single square inch.
Now the math changes completely. 100 pounds over 1 square inch gives you 100 CI.
100 times more pressure.
100 times more. We didn't add any more force. We just changed the area it was applied to. And that's the whole game. It's the difference between pushing on a wall with your palm versus pushing with a needle. Same force, completely different result.
So the fundamental concept of hydraulics is just concentrating force into pressure by shrinking the area of the piston.
That concentration is what we then use to our advantage. That's what creates mechanical advantage.
Which feels, at first glance, like you're breaking the laws of physics, like you're getting something for nothing.
It does. I mean, mechanical advantage is just the ratio of the load fun, the big thing you want to move, and the effort, the small force you're putting in.
So if you lift 40,000 pounds using only 200 pounds of effort, your MA is 200. 40,000 divided by 200.
Correct, a 200-to-1 advantage. But you're right to question it. It feels like we're just creating energy. How does that work with the laws of physics?
It works because of the law of conservation of energy. You have to make a trade-off. You can't get something for nothing. If you gain in force, you have to lose somewhere else.
And that somewhere else is always distance. Always.
So you get 200 times the force, but the thing you're lifting only moves 1/200th of the distance.
Precisely. Think of a simple lever or a car jack. You pump that handle up and down, moving it maybe a foot each time, and the heavy car just inches upward. A tiny, tiny amount. You trade distance for force.
Which makes the formulas for MA so useful. You can calculate it with forces, L over E, or with the areas of the pistons.
A out over A in.
Or even the distances they travel, ED over LD.
And the one equation that ties it all together is effort times effort distance equals load times load distance. E times ED equals L times LD. The work you put in equals the work you get out.
Yeah.
Energy is conserved.
Okay, this is where the rubber meets the road. Let's use the practical example from the sources. We have a huge load to lift, 40,000 pounds.
40,000 pounds. And our effort, what we can apply, is only 200 pounds. And we're using a small input piston with a 1/2 inch diameter.
So step 1, we calculate the MA we need. 40,000 divided by 200 is 200. We need a 200-to-1 advantage.
Which means the area of our large lifting piston must be 200 times bigger than the area of our small effort piston.
So we use that area ratio to figure out what the diameter of that big piston needs to be.
And when you run the numbers, you find that the diameter of the large piston has to be 7.07 inches.
And what's so cool about that isn't the number itself, but what it means. It means the entire performance of this massive machine is just dictated by the physical dimensions of its parts. That specific diameter is what makes the whole thing work.
But that also brings up a really important engineering point. When you're creating a 200-to-1 advantage, you're generating enormous pressures.
Right. It's not just simple algebra anymore.
No. The higher the MA, the more stress you put on everything. The seals have to be perfect to handle thousands of psi. The cylinder walls have to be incredibly strong. Simple physics gives you the ratio, but real-world engineering and materials science are what keep it from just exploding.
High MA systems are just inherently hard to contain.
Very.
Okay, so we've used this relationship to get mechanical advantage for lifting, but sometimes the goal isn't lifting a load, it's just creating insanely high pressure for a specific job.
Exactly. And that's where an intensifier comes in. It's a specialized tool. Think of it as a lever for pressure instead of force.
So if your main hydraulic pump only goes up to, say, 500 psi,
But you need 5,000 TIA for a water jet cutter or a clamping tool. You use an intensifier to step up that pressure on demand.
And it works on the exact same principle, right?
Yep.
Transmitting force across two pistons with very different areas.
It's the same math, just applied differently. So let's use the example from the source material. You have a low-pressure input of 500 CIs.
And it's pushing on a relatively large input piston, an area of 10 square inches.
Right. So step one, calculate the force being generated on that big piston. Force is area times pressure. 10 square inches times 500 psi.
Gives you 5,000 pounds of force.
Okay, now here's the key. That 5,000 pounds of force is mechanically transmitted, it's conserved,
Yeah.
and it pushes on a much smaller piston on the other side.
And that output piston is tiny, just 1 square inch.
So step two, calculate the new pressure. Pressure is force divided by area. That 5,000 pounds of force is now concentrated onto one single square inch.
Giving you 5,000 psi.
5,000 psi. You get a massive pressure jump. The 10-to-1 area ratio gave you a 10-fold increase in pressure, from 500 up to 5,000.
But again, there's a trade-off.
Of course, you get that incredible pressure, but you get very little flow. The intensifier only produces a tiny volume of that high-pressure fluid. It's slow.
Which is fine, because that's exactly what those specialized tools need. Not high flow, just immense localized force.
It's another perfect example of the conservation trade-off, engineered for a very specific purpose.
So to wrap this all up, it really seems that mastering force, pressure, and area, and that core relationship, P equals F over A, that's the key to everything.
It is the foundation.
Yeah.
And the ability to manipulate area is the single most powerful tool you have for concentrating force, whether it's for leverage or for pressure.
Whether you're calculating the size of a piston to get a 200-to-1 mechanical advantage, or designing an intensifier to get a 10-fold pressure boost, it all hinges on that area ratio.
And that fundamental law of energy conservation.
Yeah.
You never get something for nothing.
So let's go back to that trade-off one last time as a final thought for our listeners. We saw we could lift 40,000 pounds with just 200 pounds of effort, an MA of 200.
Right.
So if you, the operator, move that small effort piston a full 10 inches, the conservation principle dictates that the massive 40,000-pound load only moves, what, 1/20th of an inch?
A tiny fraction. And that brings up the final question to think about. Since we know high mechanical advantage means you sacrifice a lot of distance, what does that imply for speed?
Does high MA always have to mean slow?
Does it always mean a slow, deliberate movement? And how do engineers get around that when they need both incredible power and speed? That's something to think about next time you see a piece of heavy machinery at work.
The consequences of the math. Excellent. Thanks for joining the deep dive.
My pleasure.